So as I said, okay, we are going to talk about the electric potential. What is the electric potential? I remind you that we saw that anytime we put a charge Q that I assume to be positive somewhere, so once I put a charge Q, okay, suppose that this is your space, okay, if I put a charge Q here, what happened? It happened that this charge Q, a positive discharge Q, will create an electric field. Okay, an electric field that simple means that at any other point I will have a vector representing the electric field at any other point. These are not charges, these are just some points. Okay, at this point, for example, the field will be like this. Okay, it will be this vector, let's call it E. At this point the field will be like this. Yes or not? If you go further you go, further you go, less the field become less important. If you go very far from the charge, the field become less important. Is that clear? So how do I say less important? Means that the arrow it's less, the magnitude of the arrow is less important. So at every point we have a field. So suppose that so the field at any point, that is a vector, is equal to, we saw it last time, we says that we can write it like K multiplied by the charge Q divided by R square, okay, all multiplied by the direction of the field. Yes or not? What? No, this means the field at any point. So for example, imagine that this is the point P, this is the field at the point P, the electric field at the point P. Is that clear? Now we said that from this definition, okay, I know that somebody like to use instead of K, some person prefer to use basically 1 over 4 pi epsilon 0 multiplied by R square, okay, and then Q. Yes or not? And the direction vector. By the way, in this case here, keep in mind that the electric field is a vector at every point. Okay, then once I put a charge somewhere, if I put, so you see that it's not important to have the charge in order to have the field, to have a test charge, because this is the charge Q. This charge Q create the field already. But if I put another charge here, let's say if I put another charge at this point here, I'd put it, let's call it the charge Q1. At this point, this charge Q1 is inside the field of the charge Q plus. Yes or not? And thus the charge Q1 will experience a force, that will be the force that Q plus apply on Q1 equal to K multiplied by Q plus multiplied by Q1 over R square, where R square is this distance. Yes or not? Is the distance from here to here. So this will typically means that, but if you look at the expression of this charge, you directly understand that this part here is the field. Yeah, so the force, okay, the force experienced by Q1 is equal to the field at the point, at this point, okay, the field generated by the charge Q plus multiplied by the charge Q1. Is that clear? Okay. Now this summarizes what we saw before leaving. Okay. Now, I told you that, I don't remember, that we can also, as we define the field at every point, we can also define the potential at every point, the electric potential at every point. Later we'll understand what is the electric potential, but for the moment we just define it. So suppose also that you put a charge Q plus. This charge will create at any point an electric potential. Is clear or not? So this is my space. Here is the space. I put a charge Q, a positive charge Q, and on all the space is this charge modify the space in the sense that it create at every point an electric potential. So suppose I take this point P. This is a point P, a geometric point P, and the distance from the charge to P is called R. The electric potential, no, we use the not the E is for the electric field. The electric potential is Vp. So by definition we have that the electric potential at the point P, the electric potential at the point P is equal to minus K time Q plus divided by R. Is that clear? Pay attention. The electric potential has no direction. It means that the electric potential Vp is a number. We will understand later. So by definition it is like this. Is clear? So in fact if you this minus, okay, we will understand later that the fact that we put this minus because it will make the computation very convenient. Yes, Vp is the electric potential at the point, at any point P. Is clear? For example, if I put the point H here, we will say that the potential here will be Vh, yes or not? And so on and so forth. Okay, we have Vp equal to minus K Q plus over R. So what is the relationship between the field at a given point and the potential at the same point? So let's try to find out the relationship between the field and a given point and the potential at that point. First of all, if I have, so suppose that we have the point, so suppose that we have a point H. Okay, let's draw again. Let's say, for example, that here is the space. In this space we put a charge Q, a positive charge Q, and I take any point H in the space and assume that the distance from this charge to H is R. We know that the electric field at the point H will be equal to K divided by R square multiplied by Q plus, but we need to give it a direction, UR. And this electric field, how can I represent it on the graph? This field will be outgoing like this. This is E, this is EIH. Now but I want also to write down the formula of the potential. VH by definition will be minus K times K plus over R. That is all. So it is just a number without any direction. Now what is the relationship? Okay, what is the relationship? Try to do you can see that the field here AH is just a function of the distance, yes or not? The field change only with the radius because K is a constant, Q is a constant. So this field, the electric field, is just function of the radius. Okay, so keep in mind that if you do, so try to what if I do the derivative of the if I do the derivative, okay, I mean if I do the derivative of the electric potential, if I do the derivative of the electric potential with respect to excuse me, the derivative of the electric potential with respect to R, what do I get? If I do minus the excuse me, what is if I do minus the derivative of the electric potential with respect to the radius, it means minus the derivative with respect to R of what is the electric potential? It is minus K, so there will be minus before the derivative. It will be minus K times Q plus divided by R. Yes or not? So I am just doing the derivative of the electric potential with respect to R. So the minus and the minus cancel. This become the derivative with respect to R of K times Q plus over R. Yes or not? Now what is this derivative? We are derivating with respect to R, so so this will be K times Q plus multiplied by the derivative of 1 over R, derivative with respect to R of 1 over R. Doubts? You will, in fact, about when somebody is introducing stuff in physics, okay, you just have to wait and see at the end why I am doing this. It's exactly like in physics 1. When I start, you don't know in advance what am I going to do, but when I conclude, you say, ah, okay. Doubt? Okay. By the way, here guys, no, you were right. I made the please cancel this minus on the definition of the potential. I made a mistake. Okay, I forget please cancel it. So the definition of the potential is exactly like this. So here it will be, but here keep this minus. So this is the derivative of, there is no minus here, and so when I will do, I will keep this minus and I will keep this minus. Okay, now you know that the derivative with respect to R, what is the derivative with respect to R of 1 over R? So the derivative here is minus 1 over R squared. So we get at the end that it is K times Q plus divided by R squared. Yes or not? But this is exactly the magnitude of the field at the point H. So what did we prove? We proved that the derivative of the electric minus the derivative of the electric potential with respect to R at every point is equal to the electric field. Yes or not? So the way we introduce the potential such that its derivative with respect to R is always equal to the magnitude of the electric field, because pay attention that here there is no direction, minus the derivative of the electric field with respect to R is equal to minus the derivative of the electric potential with respect to R is equal to the electric field at this point. So we can then say is that, okay, the relationship is that the electric field at the point H, okay, is typically equal to minus the derivative of the electric potential at some with respect to R. Okay, look, this is the relation when using cylindrical Okay, this is when we are using cylindrical coordinates. Okay, remember that when you use r, the distance from the origin, you are using the cylindrical coordinates. How do we generalize this? So in general, but this is just the magnitude of the field, right? But we know that the field at any point is supposed to be a vector, yes or not? So the vector field, the electric field at any point h, in general, okay, is the gradient is minus the gradient of the potential. So this is the generalization of this. So we prove it for a particular case, and now the general rule says that the electric field at any point h is equal to minus the gradient of the electric potential. So now I will recall what is the gradient. Okay. So let's to recall what is the gradient. To remind you what is the gradient, I will do an example. Let me take a new page. An example. In fact. Okay, so never mind, guys. If you have questions, ask your question. By the way, I have earphones, so no. Okay. So I will do an example. Okay, no way. No way. Okay, so suppose that we are working with an xy in an xyz plane. Is that clear? It means that if my point h will have coordinate x, y, and z, yes or not? So the potential at any point will be function of the position, yes or not? The electrical potential will be, so I'm telling you that we have an the electric potential is given by x square plus y square minus z square. This means, for example, that the electric potential at the point 0, 0 is 0. Yes or not? The electric potential at the point, for example, 1, 1, 0 is 2, and so on. Is that clear? So I know the electric potential at every point. Now, how from the electric potential can I compute the field at every point? We know that the field at every point is minus the gradient of the electric potential. Yes or not? The field at every point. What means the gradient? So the field at every point will be equal to the derivative, to minus the derivative of the electric potential with respect to x, comma, minus the derivative of the electric potential with respect to y, comma, minus the derivative of the electric potential with respect to z. Is that clear? That is what means the gradient, guys. The gradient of a function is the vector of its partial derivatives. Let me connect my charger because the PC is going to shut down. Okay, so let's go and find such a gradient. So for the given function, the derivative of v with respect to x will just be 2x. Yes or not? The derivative of v with respect to y will be 2y, and the derivative of v with respect to z, here will be minus 2z. And thus the gradient here, the gradient of v is 2x, comma 2y minus 2z. and thus the field at any point, the field at the point x, y, z, at any point x, y, z will be minus 2x minus 2y comma 2z. Is it clear? Okay, good. Another example of relation between the potential and you remember that we saw that if we have two planes like this, plus plus, now let me put it vertically, maybe you understand it better. So I repeat, if you have some positive plate here and a negative plate here, okay, we basically we saw that moving the field in this stuff, it's always the field E between these two stuff. The direction of the field is from the positive plate to the negative plate. Yes or not? We saw this, and we basically saw this. Here are the line field, and what is, if you understand this, it means that I can fix an xy. So this is my x direction, and this is my y direction. So the z direction is going out from the screen. Okay, so this is my x, this will be my xyz system. In this case, you see that at every point, okay, I remind you that the field at every point, you see that in this case the field change only the field is a constant. No, there is no direction in which the field change. The field, whatever is the point xyz, the field whatever is the point xyz, it's always equal to what? The field whatever is the point xyz, we saw that it's always equal to sigma divided by epsilon 0. Yes or not? We saw that in this condition, between two plates like this, the field is always equal to sigma divided by the epsilon 0. So how can we then find the this means typically that you have a kind of field that is the same in any direction in intensity. Okay, so this is the magnitude of the field. Imagine, for example, here in this representation, we only have the field has only the x component. In this planar representation, the field has only the x component. So you can say that the x component of the field is sigma divided by epsilon 0, and the y component of the field is 0, and the z component of the field is 0, because we are in the plane. Okay, you see that this field go only in the x direction. So we have that the field at every point x, y, z as a vector, it is the x component is sigma divided by epsilon 0, and the other component are 0, 0. So if you want to find the potential, okay, so if I give you this, I can subject the potential at every point x, y, z will simply be the integral of this stuff. Will simply be the integral of this stuff. So the potential at any point x, y, z will just be sigma minus sigma divided by epsilon 0. Excuse me, let me write it in a better way. The potential will just be minus sigma divided by epsilon 0 times x. Why am I saying that this function is the potential? To check if it is the potential, we just need to do to check if the field is equal to minus the gradient of this function. Yes or not? To check if this function is the potential, we just need to check this. because we said that between the field and the potential, this relation should hold. If you do if you try to do the gradient of this function, what is the derivative of this with respect to x? If I derive this function, it's minus sigma divided by epsilon 0. When you multiply by minus, okay, if we put minus here and put minus here, it becomes sigma divided by epsilon 0, and you get exactly the field, because it's in the other direction. The derivative is 0 as the field is. Is that clear? Okay. Do you have any question? Okay. In fact, look, the relationship is that the potential, the relationship between the stuff is that the electric field is minus the gradient of V, right? And that simply V should be some integral of minus A. Is that clear? Because you flip the yes or not? Because this means that A is the derivative of V, so V, there is this minus. Okay, let me just cancel this. Okay, so now another aspect very important of the potential is the following. Another very important of the potential is the work of the electric field. Work of the electric field. I don't how do you, it's like this, right? The work of the electric field. Okay, look guys, when we did physics 1, I told you that typically when you have imagine that you want to move something from the point A to the point B through this path. This is a curve, right? You are moving a point from the point A to the point B, something through this curve. And let's say that on the path, at each point of this path, some force is acting. You know from the high school that the work, okay, the small work computed by a force is that force dot the displacement. Yes or not? Small work relate to small displacement. Okay, so it is possible to prove, and you should probably remember that this relationship that we saw here, the electric field equal to minus the potential, it's something that we saw in analysis in physics 1. When we saw that if some function exists such that the field its potential, we said that the field is conservative. You remember or you don't remember? We saw in analysis in physics 1 that if the field is the gradient of some function, we say that this field is conservative. But by the way, never mind if you don't remember. Okay, so I am just saying that suppose that instead of having any force F on this path, you have the electric field. Okay, having the electric field means that you want to move from A to B, and at every point there is some electric field. Okay, we want to compute the work of the electric field from A to B. So this is the work of the electric field from A to B. Is that clear? What I am not going to prove, but this work is always equal to the electric potential at A minus the electric potential at. Is that clear? So the work of the electric field from A to B is always equal to the electric potential at A minus the electric potential at B. What does it mean? For example, suppose that this is the kind of stuff that come at the exam. So you have a charge here, a charge Q1 here, and Q1 is it's like the source, okay, the sink, the one that create the field. Suppose that the question is this is my charge Q1. At the beginning there is no other charge in the field created by Q1. Then we suppose that there is some charge at some time. So at the beginning, no, we have the charge Q1, but we have another charge Q2, but at infinity. When we say that we have another charge Q2 at infinity, it means that they are very far one to each other. Okay? So at the moment, they are so far one to each other that they cannot feel the effect of, one cannot feel the effect of the other. Is that clear? Then, so this distance here, the distance, the initial distance is infinity. Then at some time, my charge Q1 is at the same position, and we bring to the distance D the charge Q2. What happened? It means that initially, what was the potential, what was the potential of Q2? The potential of the charge Q2 was K multiplied by Q, because by Q1, because the one that created the field is this one, yes or not? Divided by what? What was the distance? Infinity. So the initial potential was 0. Doubts? Then at the end, what is the final potential? The final potential of Q2, okay, let me call this is VA when Q2 was still at the point A. Now at the end it's at the point B, yes or not? So VQ2 at the point B will be Q1 divided by D. Yes or not? The question is, what is the work of this electric field? The work of the electric field during this the motion of the charge from here to here. It will just be VQ initial, so VQ2 A minus VQ2 B. That will just be minus Q times Q1 over D. Is that clear? So you should be able to, when you move a charge from a position to another, the work of the electric field is the initial potential minus the final potential. Finally, we talk about the potential energy. No, not finally. We talk. By the way, we talk about the potential energy. Okay. What the potential energy is? We already says that at any point, if I take a point H, suppose that you put a charge Q somewhere. You put a charge Q somewhere, and suppose that this is the space. At any point of this space, there is a field, there is a potential, and so on. Yes or not? So the potential at H, the potential at H will be, as we said many times, K times Q divided by R. Now by definition, by definition, if you put some charge Q1, okay, if you put some charge Q1, at H, the electric potential energy of the charge Q1 will be exactly Q1 multiplied by the electric potential at H. You understood the point? So when I put a charge somewhere, the electric potential energy, this is the electric potential energy, the electric potential energy of that charge will be that charge multiplied by the potential at that point. This means, for example, if at some point I know that the electric potential is 10, and I put a charge Q1 equal to 10 coulomb, okay, the electric potential energy of the charge Q1 will be equal to 100 joule. Okay, now we saw that, so the electric potential energy it's equal to the charge multiplied by the potential. Exactly as you should remember, the electric force is the charge multiplied by the field. Okay, this is some kind of duality. Okay, it turned out to be some kind of duality. Okay, you will ask me, like, about all this stuff that you are saying, what should I keep in mind for the exam? What you should keep in mind for the exam is, for example, the definition of the potential, okay, that we gave, the relationship between the potential and the field, and the relationship between the work of the field and the potential, and the definition of the potential energy, and finally, so we all this relation that I'm going to give now. So we see, for example, that the electric force applied to any charge is equal to that charge multiplied by the field at the point where the charge is placed. Now what I want to tell this duality, we saw that the work of the electric field is VA, is the potential at A minus the potential at B. Yes or not? By the work of the electric force is the potential energy, okay, at A minus the potential energy at B. So there is a kind of duality. The potential work with the electric potential deal with the electric field, and the electric potential energy deal with the electric force. Is that clear? And we can even say that the electric force is minus the gradient of the electric potential energy. Okay, to summarize and leave and close down with this stuff of potential. To summarize, the field at any point, so when I put a charge Q, suppose let me summarize on a new paper. Okay, so suppose I put any charge Q somewhere. This charge create a field everywhere. The field at any point P, okay, will be equal to K times Q divided by R square multiplied by the direction of the field. The potential at any point P would simply be equal to K times Q divided by R. Okay, the the relationship between the potential and the field is that the field at any point P is minus the gradient of the potential. Okay, then we introduce we say that if you put another charge Q1, if you put another charge Q1, this charge Q1 will experience some force. That force will be equal to Q1 multiplied by the field at the point where we put Q1. Then from this force we also define the potential energy. We also define the potential energy of the charge Q1, that is also equal to Q1 multiplied by the electric potential where we put at the point where we put Q1. From these two relationships also we saw that it holds that the force on the charge the force on the charge Q1, the force in general, the force at any point, is equal to minus the gradient of the electric potential. Okay, the minus of the electric potential energy at any point. Okay, hello, this summarizes the stuff. So these are the formula you need to know for the oral exam. Yes, the work, excuse me, I forget about the works. That the work of the electric field from a point A to the point B is VA minus VB, and the work of the force and the electric force from a point A to point B is the electric potential in A, and is the electric potential energy in A minus the electric potential energy in B. Okay, now this summarizes all. Very last thing about potential, very last thing that you that are called equipotential surfaces. Okay, because they are equipotential surface. What is an equipotential surface? Now it's time to suppose that, guys, I put my charge Q here. Okay, if I draw a circle around, if I draw like something like a sphere around Q, look, all this point on this sphere, what is the distance? What are the distance of all this point from Q? The distance is always R, right? So let me call this distance big R. Okay, it's constant. So all the point on this, all the point belonging to all these points here, they share the same distance from yes or not? So the potential, okay, V of VP, so the potential at P, or if you want, as I said before, VP is equal to K times Q divided by R for all P, for all the point belonging, let me call this surface S. So this surface is S for all the point belonging to S. Yes or not? You see that all the point belonging to, as they all differ from the same distance to Q, they all have the same potential. Yes or not? Can we say that they all have the same field? No, they have the same field in magnitude but not in direction. Yes or not? Because the field, for example, at this point will be like this, whereas the field at that point will be like that. They will have the same magnitude but not the same direction. Is that clear? So all the points on this stuff has the same, all the points on this surface has the same potential. So what do we call equipotential surface? Equipotential surface are surfaces where all the are surfaces with all the where all the point has the same value of the potential. Okay, so this surface here is an equipotential surface. Okay, and equipotential surface is a surface on which there should be maybe an edge, but on which all the points has the same electric potential. Is that clear? Okay, so if the field is created by a single charge, the equipotential surface are the spheres, yes or not? Are spheres if the field is created by a single charge. Okay, any doubt about the potentials and the related stuffs? Okay, nice. Before moving to dipoles, we will have a break, but before the break I would like to let you see a kind of exercise that you may find in a book. So suppose that I put some three charges like this. This is Q1, this is Q2, and this is Q3. Let's say that Q1 is minus 2 coulombs, Q2 is equal to 3 coulombs, and Q3 is equal to let's say 4 coulombs. The question is to find, so this it's like to say that the three charges are on the vertex of a triangle. What? Excuse me, it is Q2. Okay, doubts? No doubts. So we have these charges, and we typically want to understand, we don't want anymore to understand the force that everyone applied on other, because on the first chapter we fixed that. Now we typically want to find the total potential energy of this configuration. I want to find the total potential energy of this configuration. Remember that you should believe that between two charges, okay, so when finding the potential energy between what is the every charge, they are interacting with together, yes or not? So you have the interaction of Q1 and Q2, you have the interaction of Q1 with Q3, you have the interaction with Q2 and Q3. Doubts? No doubts. We already I remember we understood that. Okay, for every pair of interaction you can choose one as the sink and the other one as the test charge. Is that clear? If we choose, for example, in this interaction Q1 as the sink, the potential energy of the configuration, the potential energy of this couple will be, so as we are choosing Q1 as the sink, it will create we will take the potential of Q1 multiplied by Q2 to get the potential energy, yes or not? So it will be K Q1 over the distance between the two charge. Let's call it for example, let's call this distance D1, let's say D12, okay, D23 and D13. So you see that this will be divided by D12, yes or not? So it is, let me write it better, it is K Q1, yes. No, just let me just, no, look, this will be the potential multiplied by the charge, yes or not? That gives the electric potential energy of this couple. Then you see nothing changed if you consider Q2 as the sink. The same you will do for the other couple, Q1 Q3 divided by D13 plus K Q2 Q3 divided by D23. So this is the total potential energy of this configuration. Is that clear? And remember that the variation of the potential energy, if this configuration flip, okay, if this configuration flip from, if something happened and this configuration, if you have an initial configuration and then due to something it flipped maybe to a new configuration, let's say that the new configuration look like this, it flipped to a new configuration that may be typically, okay, it flipped maybe to a new configuration like this. I don't, now this is Q2, Q3 and Q1. Now look that the system flipped from a configuration to another. If the question of, if the exercise say compute the work of the electric force, you just know that the work of the electric force is the initial potential energy minus the final potential energy, because it's very complicated to go and understand what happened in details. Okay, the work of the electric force will just be the initial variation of the potential energy minus the initial minus the final variation of the potential energy. I did this let's say this stuff very in details. So if you don't have any question, I will stop here for the potentials, and after the break I will start talking about the dipoles. Okay, we have a break of 10 minutes. Okay, see you then, guys.